which you have done, if any of you can show me the results, that will be good to see. Because
Okay, okay,
so
sir.
let's have a look first, and the third last part, which you were saying, the interferometry part, that I will again talk about. So,
Okay, okay. So, Bipradeep, can you share your screen? Bipradeep, are you there?
Yes, ma'am. Just a second.
Okay. Initially, sir, we were thinking that we will leave this experiment
mhm,
because this was discussed the last in the series of experiments, and then we were allotted
mhm,
this one. And now
mhm.
it appears that this is more interesting than the initial ones.
Okay, 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 good.
So one of the students of the first group, Bipradeep, he is sharing the screen and we will discuss our findings along
Yeah.
with that.
Uh, 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 I cannot present. I mean, the host has disabled participant screen sharing.
Oh, Prakash sir will give you the rights. Prakash sir.
Yes, sir. Sir. I hope it's visible now.
Yes. So we can start from the beginning, maybe from the Gaussian.
Yeah.
Yes. So the first part is clear to us,
Mhm.
and like
The first part was that we had to determine the frequencies of these Gaussians, the multi-component H1 line.
Yeah, yeah. So
So that was
Vipradeep,
fine.
have you been able to fit a set of Gaussians to it?
Yes, sir.
uh,
We
yes,
fitted two
ma'am.
Gaussians each. There can meaning you said we can fit three, four Gaussians, but we started with only the two main, the
Okay,
highest peaks in both
okay,
of them.
okay. Yeah, that's fine. So let's look at them after fitting what happens.
So the fitting is done by ma'am, but I've tried to fit a overall Gaussian to the plot,
Okay.
which it looks like this.
Yeah. So that is,
So
yeah, yeah. So that is useful still, that you can see that what is the peak is close to the actual peak. So that is useful, that what frequency it is emitting the most. So that becomes clearer. And the
Mm.
broad wing may need meaning. So there would be few lines and so on, but yes, it does give you an idea that, but only thing is that if you want to compare with the narrow lines, which is in absorption, because this line, Gaussian being a single one, it is artificially wider.
Hmm.
okay,
And in the emission spectrum, we got the width was more as compared to the absorption spectrum.
Yeah.
And as you mentioned in your previous session, that
Mm.
is expected also. Meaning for
Right.
the absorption, we got the width as 0.013 megahertz. And for the
Mm.
emission, we got it zero point 0.5 megahertz.
Mhm, mhm.
But somewhere you said it will be 1 megahertz. So
No, no,
is
no, no. I have
it
never said it will be 1 megahertz. The point is
meaning
that
something?
most of the emission occurs in that 1 megahertz regime. That is what is the
Okay.
case. And the RMS
Okay.
also may be higher in that the frequency range.
Okay. Okay. So first point we are clear with. So now the second point, Bipradeep, second one. So in
so
the
in the
second
second
we
part, we divided the spectrum into five parts,
Yeah.
uh, uh, and then calculated the RMS from each of the segments.
Right, I think that is still reasonable. What I might have done is to put kind. It looks like, if I in the meaning that this is essentially there is a sinusoid of kind of thing. So either put the second order polynomial, or even better maybe a sine omega t, meaning sine theta curve, that where basically the sinusoid goes away. If the sinusoid would have gone away, even you can take the whole region. But what is important is to check what you are doing is also fine, but there you may be at, meaning what I might say, that like the S3 region, what you have divided is pretty narrow and pretty flat. The base level looks pretty flat. So there the
Yeah.
RMS would be reasonable, whatever you find. But on the other hand, like S1, it has got a slope. So there the
Yes.
RMS, whatever you find after subtracting the mean, that is x minus x average whole square, once you do and sum them up, that will be the meaning that will have contribution because of the slope. So that may not represent the true RMS. So places like S3 or even S4 may be reasonable for whatever RMS you find. So like S3, you can the fit test meaning A plus whatever, meaning just a constant term, and you are finding the RMS value around it. So if you just fit S3 by your Fx is equal to A, that itself would be good enough. And what is the error on A?
Okay, sir.
But only thing is that you have to keep in mind that the error on A, suppose A is just a base level you are fitting, which is here of course close to zero, but exactly not zero, I can see slightly negative. But the thing what you have to remember that in a plotting program, when you are asking for finding the mean, because it is finding the mean from say using 10 data points inside S3, let's assume there are about 10 frequency channels within that. So what will happen is that the RMS, whatever A will say, give you some, let's say number, which is zero plus minus something, plus minus 0.1, whatever it is. So that number has been artificially brought down because the mean of a sample would be essentially going as 1 by root n times the individual sample RMS. So the RMS of mean goes down as 1 by root n, where n is the number of samples in that mean. So that you have to keep in mind. So the actual RMS for individual sample will be higher by root n.
Okay, sir.
Mhm.
And so we tried to do a calibration, like we calculated the RMS from each segment and then subtracted it from the signal to check like how close it's to the baseline. So, and before doing that, we tried like what if we calculate the mean from each segment,
Yeah.
then subtract it and then do the RMS calibration. So we found that it brings the signal more towards the baseline.
Right, right.
So
So
what do you mean by RMS correction?
I calculated the RMS voltage for each segment and then
Yes.
subtracted it
No, you
from the
cannot
signal.
subtract that. That's a statistical quantity representing the fluctuation. You can use that to scale, okay, but not subtract.
Okay, sir.
Means can be subtracted. RMSs cannot be subtracted. Okay.
Yeah, in fact, I
RMSs can
was
be used
wondering
to
that they
scale
meant
the
mean or
thing.
RMS. Yeah,
Okay, okay, sir.
yeah.
We will fix that. And similarly for the part 3, like we took the same segments and calculated the RMS.
Yeah, so here there is a line. The issue is only that at the position of the lines near 1420.5 megahertz, you don't know the RMS. So there, if you notice the frequency within that regime, within say that 1 megahertz or 2 megahertz, it will be useful to check if the RMS is higher. You go back to the previous plot. So S3 region, I think the S3 region has a higher this thing.
Yes.
Yes,
Has
it
a higher RMS, I believe.
yes, it had a higher. We can
Yeah.
you can show the numbers also, Pradeep.
Yeah.
The 5 segments
Yeah.
was there before this, yeah. And definitely there we have more variation, so we expect a larger RMS in that region.
Yeah. No, in fact, that you have to see that
Is it an
actually.
absorption?
Is it? Sorry.
Is there an absorption there at those frequencies?
Yeah.
Yes,
And
this is the absorption one.
Yeah. So if there is absorption,
Mhm.
won't you expect the system temperature to be lower?
Yes, it will be lower.
And
Then
hence the RMS variation to be
should
lower.
be low. Then it should be low because that's upon the sample.
Yeah, it just so happens that it's
Mhm.
also the region where the H1 emission might be there.
yeah.
Okay.
Okay.
Is not captured by this, okay, because it's resolved out, but leaves the noise.
Okay.
The
Okay.
fluctuations associated with the increased system temperature
Mhm.
due to the H1 line emission,
Emission.
okay, might contribute heavily.
Mhm.
In addition, so it's a combination of both. Okay,
Both of
reduce
them.
intensity of the background source because of the
Mhm.
absorption,
And emission due to
and
the
the
H1
increased
beam.
emission due to
Mhm.
H1 emission. Okay.
Okay.
Yeah, in
So,
fact, one
So
way to
here,
look at it would be that if you go to the emission spectrum, just go there once. Yeah, so if I look at, well, the number, I'm not so sure whether it is calibrated, but I believe the number 0 is actually meaning, I don't know now, I don't remember that whether I gave the numbers after subtracting the baseline, because
yes,
normally,
yes, yes. Yes, it was 700 to 1000 something. And
okay,
then in your session, it was from 0. So we subtracted a constant and
okay, so
scaled
that
it.
number, the mean which you have subtracted was about 700.
Yes, it was around 700.
Okay, so you can see that 700 becoming 1000 at the peak. That means about the whatever 30 the divided by 70, which is more like 1.5 times. So the
Hmm.
system temperature, which is typically 70 Kelvin for GMRT in L band, would
Hmm.
become 100 Kelvin at the peak of the line. Okay,
Yes.
so
Hmm.
100 Kelvin means you can expect also about 1.5 times noise in the
Hmm.
S3 region compared to the rest of the spectrum.
Okay. So,
And why
say,
it is important is that this offshore spectrum, because suppose you want to publish something
hmm.
using this kind of strong H1 line, you
Hmm.
find something, when you quote the RMS, you have to look at this increase in system temperature. What they showed or told you is because of that, that it is
Hmm.
important. That is the implication that you should quote the correct RMS, which will be using offsource, not just using the baseline level RMS.
Okay. Okay.
In fact, much like the mean intensity profile that you plot as a function of frequency,
Hmm.
customarily, it's also useful to plot the RMS profile in frequency, okay, which you will
Hmm.
see will follow the system temperature variation.
Right,
Okay.
right, right.
The net system temperature, meaning
Yeah.
emission minus absorption, meaning like we had in the S3 region.
Yeah,
Yeah. Okay.
of course, if the source is not very strong,
Hmm.
the absorption of that source intensity at certain locations may not
Hmm.
drop the system temperature significantly, while the H1 emission might be pretty significant, and
Significant.
that might dictate the essential variation in the system temperature.
So is
And
this
yeah,
uh, so is this obvious from these graphs also, meaning the absorption scale is from 0 to -5, and meaning are they normalized numbers or
yeah,
meaning
if the
can we
scales
compare
are
them to?
similar, okay, then of course
Yeah.
you can see that you had almost you know 300 units of increase in the system
Emission?
temperature, okay,
Hmm.
whereas due to the absorption the system temperature decreased by only 5 units.
So do we need to do any rescaling of these numbers, or can we compare this 300 scale of 300 with a scale of -5, meaning
Well,
5?
overall, to get it to some absolute scale,
Hmm.
as Shubhashish said,
Hmm.
that if the pedestal was about 700, and that
Hmm.
really corresponds to about 70
Hmm.
Kelvin
Hmm.
of system temperature, then some amount of rescaling to
Okay.
bring it to, but if this is expressed in Janskis and it's arbitrary units, then of course, relative comparisons can still continue. But if you
Okay.
wanted any absolute,
Yeah, I think
uh,
these are probably now absolute number. The meaning these are reasonably, meaning these are calibrated data.
right,
Even
right,
the self in that sense should have got calibrated.
okay.
Though we have never checked the self, whether the calibration is correct for self. We have checked it for works for cross, that's fine. For self, in principle, it should be. In practice, I never know it has, and I've not, meaning I don't think anybody has tested it for that with GMRT. But one thing I think I think the point which Chetna was saying, that that what I would say is actually that the absorption part, whatever you were saying, that suppose there is an absorption, that
Hmm.
should also be reflected in the total power. Okay.
Yes.
So whatever you are saying, so suppose that source, the background source would have been like not say 5 Jansky or 7, the background source is 7 Jansky, rather than suppose it was 700 Jansky, which is equivalent of about, let's say 200 Kelvin of
Hmm.
system temperature, because it's about 0.3 Kelvin per Jansky is
Yes.
what the scaling for GMRT is,
Hmm.
with the typical sensitivity, whatever we have. So that would essentially corresponds to double the system temperature. So that would be also reflected here in the total power, because this is also total power in that sense. So any absorption by the background source at the H1 the frequency would be accounted for already. So you don't have to account for absorption when you are talking of the total power or the system temperature what you have seen.
Okay. Okay.
It is everything is reflected in the total power data. You
Okay.
don't need to look at the cross.
ठीक. Okay, so this is done. We were at RMS of the entire program.
Yeah, so we divide it in the same segmented, and then
The other comment I wanted to make, that the total power, which the spectrum which you showed, I recall that there are actually two polarizations present. One is
Yes.
RR and one is LL. I think what you have plotted is the RR one,
Yes,
right
yes.
circular polarization, which we normally call it, though I'm not sure whether they are really right or left. There could be the missign convention, but whatever. The LL, I believe, was better behaved, the baseline. The baseline here, there is a slanting angle I can see, but that was not there for ALL. So you
Okay.
could use any one of them. I thought I had taken out the RR one, but anyway, whatever is there.
Meaning the file had both of them, so we took only the RR.
Yeah, so
polarization.
LL, if you take, that would be better, meaning in that sense, the base level is the more flatter.
And why is that so? Meaning, why is that more flat as compared to the
Yeah,
RR?
it is a matter of coincidence. We don't know, because normally the issue is for a telescope, like say interferometer, is designed for interferometry. They are not designed for doing total power estimates. Okay, though the reverse is not true. That means if a telescope has been designed for total power experiments, you can certainly use it for cross, but not vice versa. The reason being that the side lobes level and so on are very well determined for single dishes, whereas for GMRT that may or may not be true. So we don't know. So
So
the
do
thing,
we have this kind of a flat thing for the left polarized for all the sources for all times, or meaning is it only for this particular case? In general, we always get the left one is the baseline is more flat
yeah,
every
here
time.
that was the case. I can't say, because most often nobody looks at the total power, as I said, because the reason being, it is the telescope is not designed for that. The side lobe level may not be well meaning side lobe
So
level
this
has to
can
be
be
well determined, and the thing is how much is the contribution coming through the side lobe, one has to know. So that is one. Then there are things like yeah, so the
okay. So this can vary. There is no
meaning
set.
ideally both should tally each other. Ideally, if we just go by gain, that is G mu the ij or the G mu nu, whatever you call it, if you do that, then the GII or the GJJ should basically you should be able to make it
They
flat
should be
by doing a
matched.
bandpass calibration with cross data. That is
Oh.
what I had done, but then yeah, in practice it may or may not.
And is this difference considered as a significant difference, or this
I
is
don't know,
negligible?
because nobody for science nobody uses the total
Nobody.
meaning,
Okay.
well, I should not use the word nobody, but to my knowledge nobody uses the self data for doing science with JMR.
Okay. Okay.
I think that the differences in the way one calibrates might actually account for this very easily, and might be calibratable, except one may not pay great attention to calibration of the total power or the self correlation as much, because you can have self correlation where there is a DC pedestal corresponding to the receiver noise, and in addition you have the sky signal getting amplified in certain way.
Yeah,
The summation of the two, the relative importance of it, might decide whether a simple division will work. It's like if you take something where you're trying to calibrate gain, but it has an offset due to something else, okay, additional system temperature, you know that dividing by the number which is not scaling with respect to the gain, but has an offset, is not a good way to calibrate.
Calibrate.
So,
Yes.
so things like that are small, subtle things. If they are taken care of properly, it will, all take care of itself. And one can invert this differences and get everything on the same footing.
Okay.
But one doesn't pay so much attention to that, because that will require a reference measurement to be done when you're just looking at the receiver noise alone, okay, by giving some particular input and so on and so forth. So all those measurements not having been done for the single dish, because these things don't matter too much when you do the cross correlation, because the pedestals due to receiver temperatures don't figure in the cross products.
So, so like in X-ray analysis, when we are not sure about the calibration thing, then we compare the flux with respect to Crab pulsar.
Right.
Is
So
so
similar thing done here as well. People
okay.
use calibrators
Mhm.
to characterize the system and use that to correct for effects that the instrument introduces, okay, by
So
using a template of known source.
so what is the calibrator here, which is generally used? Meaning in X-rays, Crab is a standard source. So is there any fixed calibrator here, or meaning what
Yeah,
is taken as
Shubhatish
a
can
calibrator
probably
in radial
answer
data
that, what
analysis?
calibrator he has used to calibrate this.
Yeah.
Or
So
in
the
general, which do we use?
yeah. So for H1, as such, since this is galactic H1, it is there all along the galaxy. So you will
Hmm.
have a problem of bandpass calibration. But what I had done was to use something called 3C287, which is a third Cambridge catalog, the
Hmm.
source number 287. So that is at a very high galactic latitude of close to about 90 degrees. So you're looking almost up. And we
Okay.
know that the H1 line, which is seen towards the direction,
Hmm.
contributes to less than 1%. So
Hmm.
that's why there you can safely do using that source for bandpass calibration. So that reasonably takes care of it.
Okay.
But
Okay.
yeah, Desh is absolutely right in saying that, because in total power you have the contribution from the sky and
Hmm.
sky temperature, whatever. Though I think in L band the sky contribution, that is in 1.4 gigahertz, is pretty low, but it has its own spectral index. That is an issue. So that little bit of slope can come even from that. But generally, I think that sky contribution I expect to be pretty low at this.
Okay.
Yeah.
Okay.
Yeah. So one thing in this plot which you are showing me, I just noticed one thing, that see that S3 region, when you have line, it does not carry any sense to quote RMS where the line is, or go within the region where there is line. So you
Hmm.
should never quote an meaning. There is no point doing that, right? Physically,
Hmm.
because the RMS does not carry sense, because whatever you
Understood.
are doing is systematic deviation because of some physical reason. So S3 region carries no sense. Other regions, yeah, that's fine.
So in this third part, we were supposed to determine the RMS for 30 seconds data, 5 minutes data, and the whole array. So
Right,
that was basically with respect to the baseline, not the S3 region.
right, right.
Okay.
So do you see it scaling with what you expect? Do you have an expectation that with respect to integration time, how the noise should go?
Yes, it should reduce from 30 seconds to 5 minutes,
Yeah,
because we saw, the the more variation, the purple one, purple one is the 30 seconds, yeah. So there the variation about the mean is more. So we were thinking that it will have more RMS as compared to the other one, the green one, which showed all the variation about the mean value only. And then for the entire data, it again increased. Do we have these numbers? Yeah, numbers are here.
So Shubhashish, they have data which are integrated for short intervals and many such spectra, right?
okay, I had given them essentially just for one. I think three baseline I have given. I think.
No, no.
Uh,
Even for given baseline, do
hmm.
they have data which is available as a dynamic spectrum?
No, I don't think I have done that. I don't think I
I
did
think.
that. Uh,
No, no.
So
uh,
how many spectra do they have to average? When you say 30 seconds, 5 minutes, and
no, no. So
complete?
5 minutes and so on, I have averaged, and I've given them the spectrum separately.
Oh, you have given them.
Yeah, yeah,
Okay.
yeah.
No, no. I was wondering if at any given frequency, do they have an ensemble of points
Hmm.
that they can estimate RMS on?
So in that 30-second thing, okay, this is 30-second data. No, I did not do that. I think the I did not do that. So these are
No, no.
basically.
Do they have access to that kind of data where they can compute their own RMS, right?
No, we had only this file where it had two columns, frequency and Jansky. So we have only plotted this data. We have not done
Okay,
anything
okay,
with this
So
okay,
it
separately.
okay.
would be for
Yeah,
RR and LL, two polarizations will be there.
okay,
So that they can do separately. And also,
okay,
I think for 30 seconds data, I have given for three different baselines. As far as
okay.
I recall, these are probably for three different baselines, I think. Let me just,
No, only single baseline. I think there was only single baseline. One
yeah,
to
actually,
16.
that's correct. Yeah, yeah, 116 with 30 seconds of data
One
average.
to 16. Yes.
The same, because I'm giving the same baseline with 5 minutes of data average
Mm.
and using data for the whole array, which is basically vector average. But
Mm.
then with the single the thing that is basically a single baseline,
Mm.
you have data as a function of time, right?
Yes.
Yes. Yes.
So that time is there. So
Yeah.
basically,
So how many time samples are there for each channel, roughly?
You can
mm,
find out Pradeep by the length of this file here
let
only.
me just open the file
It
also.
is 213 or something, 231. We don't remember.
Okay, this is as a function of frequency. Sorry, no, no. The time is the only. This is one timestamp which
Time
I've
was
taken.
in the
Yeah,
index, the first
yeah,
column
yeah,
of that file.
yeah, yeah. So it is basically just the one time, the snapshot, one time scale of 30 seconds, which has been given for a
Oh,
single baseline. For
okay,
the same baseline, I've also averaged and given them.
okay, okay. Yeah.
Yeah.
Right. So
So
they don't have access to do any statistics on individual channel data.
individual channel data, I can give them. I can extract and give it to them. But the as such, this is not given to them right now.
Okay. Because if that were to be available, then
Hmm.
they could compute the RMS for each channel and
Hmm.
plot that, and that will follow the system temperature profile.
Right. Yeah, yeah.
Is it possible to give us that file?
No, I can give you the feeds
Maybe?
file, but the problem is that UV feeds file, how do you work on? Because that is the issue. You have to either take
That
them
we'll
to
take care of. That
apes,
we'll
or
take care of. Meaning we'll try to take care of that.
if any
Mm.
one of you knows any astronomical the software like the CASA or apes, then it is okay. Otherwise, how will you extract the data? Because in from a typical feeds file, you can't
Mm.
normally extract the data as such. There would be data of all sorts. But then for those baselines, you can extract.
Okay,
Otherwise, I have to extract, but then the
send
issue
us
is
the data. I'll try to convert FITS file to ASCII so that students can learn something out
no, no,
of that.
that will become too big. So that is the issue because
Oh,
this is like 100 MB file can go to many other several GB, and so those things right now what I'm looking for is that the meaning there are many things possible, but the zeroth order thing whether you are understanding. So I have given from that viewpoints. So the zeroth
okay.
Yeah,
order
yeah.
like I'm asking that
Sorry, I didn't mean to distract. I was just trying to understand whether they had access to
yeah,
the
so
And
I
we
can
thumb.
make it available, but the issue is then or I can extract or the one frequency channel as a function, but you want then effectively all the data basically, right? Because
mm,
it has to be done like
for all the
Yeah,
channels.
I think what I meant was if simple dynamic spectrum for a given baseline,
mm,
okay, was available, where you had frequency on one axis, time on the other axis,
Mm.
and that they could play with.
yeah,
How
But
to
anyway,
convert
that
it
so
to
is
channel.
difficult to
don't.
extract
Yeah.
in ASCII format for me from my side. That is what I've seen that time. So the thing is, yes. So I have basically done it in somewhat focused way. So these 30 seconds is basically. So Chetna, can you or one of you rather? I'm not asking you as such. The group rather.
Mm.
That can one of you tell us that how the RMS should go down as a function of time or integration time?
So it should reduce with the integration time.
No, that's correct. But
Any of the
by what factor?
students should tell this. May 1 by root n, the number of samples in that data length.
You were asking me.
No, no, meaning I don't know.
Okay. Yeah, yeah. No,
Whether
you
I'm
are asking the
asking
students
you
probably. So if they keep quiet, I will
the-
tell yes. So it will basically go as 1 by root t, the integration time. So 30 seconds to 5 minutes. So it will go like that.
So we have to check these numbers also whether it went like that or not.
Yeah, meaning because that is what I would.
Roughly it should match with that.
Yeah, yeah.
Rule. Okay. So this is also clear to us now. And next is the fourth one, which we did not understand at all, where to start and what to do.
Okay, the fourth one is basically,
Maybe Bipradeep Sahil, do you have any other query till this point? Otherwise, we'll request sir to explain us
No,
the.
ma'am, no, ma'am.
No, ma'am, we don't have.
Okay.
okay,
Desh sir or Subhashi sir, can
yeah,
you, meaning it's
yeah,
a
yeah,
small request,
yeah.
can you hold another school for the statistical analysis also? Is it possible? Is it possible? And that should be with a whiteboard in the background so that you do the calculation also in front of us. Meaning sometimes things are lost in air. Is it possible to do that? Or maybe you can summarize Bevington for us, because students also faced some problem here and there.
Well,
Somebody has written, somebody
well,
has said yes also. Yeah, that would really be good.
yeah, it's possible to arrange that such a thing. Maybe just a couple of lectures would do. It may not have to be a full school.
Meaning for you, it will be a couple of lectures. For us, it will be at least
No, it
one
can
day.
be done slowly, spread over
Mhm.
a week or something. Yeah,
So that for
if
for
you
every
any one of you
calculation we
would
need
wish
not,
to arrange that, we will be happy to help. I mean,
because here for every calculation we are going to Google and looking at the definition and then coming back. We want
But
it
I
on our
see in
tips
your
every day.
schedule that on Saturday, last Saturday, January 2nd, basically, Ranjit Mishra had taken a class on error analysis.
Is he in this meeting? Our group did not follow that at all.
Okay, okay.
We want something from Desh sir and Subhashi sir, because we are understanding
No,
the way.
right now, whatever I have given, if you understand, meaning, okay, there are two things. One is the interferometer. I will not, meaning, it is expected that you will get stuck. But
Hmm.
in general, just for RMS calculation and so on, what we are expecting, as I said, like one by, meaning, as you already said, that it is the root over of one sample. So
Hmm.
that sample, when it is going 30 seconds versus 5 minutes, you know that 30
Hmm.
seconds, if there is one data point, or the 5 minutes will have about 10 data points. So it
Yes.
is like that. So root and n root 10, it will
Hmm.
improve. So it is
Hmm.
like that. So similarly, the same case, same thing applies for frequency channels or the number of baselines when we talk of. So when it has come to full array, it is like that. Now that is the at the zeroth level. That kind of thing is what you need for this kind of a thing. But
Hmm.
yes, on the other hand, if you are talking of general error analysis of experimental results,
Hmm.
that requires a bit more, where it needs things like error propagation. So those things you have to do. And but then again, the I think it has been done even last year also. This year one class was there. Probably you needed something more. So it is a feedback which I think this program we should take basically from you, that we should perhaps have couple of lectures at least on error analysis, and starting from on the going slow, meaning
So
the
will it be fine if we say that we want those sessions from you and Desh sir? Meaning we are not
actually
attending
I
anything. We
I
want
don't
to
think I
see
will be
both
able
of
to do
you.
that. But on the other hand, if this can do it, it's fine. Or otherwise,
Because Desh sir
somebody else
does
can
the
do it.
calculation so quickly, and meaning we want to be at least 50% as expert as Desh sir. I don't know what uh, if it is possible, even if not a school, 1 day or 2 day, or depending on who are the participants.
yeah, I mean, if Psyche would advise, I would be happy to give an hour lecture in the evening on how in practice one plays with these things. And uh,
Meaning very small things, like when we were doing these OT data analysis, everything. So we had a
right.
Gaussian, and then students got stuck. What is meant by RMS of a Gaussian distribution, and what is meant by standard deviation? Although these things are we have studied uh,
Yeah.
now and then,
So
but
in
still
stating
an
several things,
overview.
we might have presumed certain
Mhm.
things,
Mhm.
which if you think are worth clarifying, one can do one can actually do a corridor session in the evening, right?
That
And
should come with a blackboard also. You should be there
Uh,
on the blackboard or a wide
okay,
meaning.
maybe there is. Yeah, I'm not familiar with the softwares which allow that, but I think in Words one can do that. There'll be enough pictures to illustrate things.
Meaning like when we are taking averages, we can meaning you can say, okay, the five numbers are 2, 3, 4, 5, 6, and now we do some statistics on that. Meaning the voltage series, the real voltage time series, these come later on, so that
Yeah,
everything is
yeah,
a
one can
basic.
actually, walk one through,
Yes.
we can walk.
Meaning assuming that everyone is only class 12th pass, we don't have any experience that way. Whenever, meaning not in this school, maybe some other day or at your convenience.
Sir, is it possible to have a course similar to what Dr. Jean Sudresh took, like on exclusively on data analysis? Hello.
Hello.
Okay, like I was asking recently, there was a course on optical interferometry
Hmm.
arranged. So, is it possible to take similar course on data analysis of this type of data?
No, I understand that, but again, I don't think the yeah, yeah.
So, because actually this data analysis was kind of complicated thing for us, uh, and like in this time.
Hey, sorry, when I asked Saikia the question, just at that moment, I lost the network because of power failure here. So did Saikia say anything, or Prakash, do you have any? I, okay. So can Prakash, can you repeat what you said? Because I joined just now. Right.
So similar to the course that recently happened on optical interferometry. So similar type of a course like on data analysis.
Yeah, I think that is what is right now makes sense because the on the spot we can't decide things, and so the thing is, it is good to have the feedback, and then that feedback one can work on, and I think then NRC can work on.
Yeah, if they need an immediate discussion, much in the connection with what they're doing, uh, I'm happy to spend a couple of hours, uh, clearing their doubts or walking together through some of the analysis. Maybe one can do that after.
Okay, so let me come back then to the actual thing because some of you have said that this interferometry part is not at all clear to you. So should I go ahead with that?
Yes, sir. Yes.
Okay. So the point is I will do a screen share right now to show you one point. Uh, So I believe you can see that this is something which I had shown the meaning. I have not meaning I wrote down the equation and so on. This one, this f is equal to cos 2 pi nu tau g. This thing I had shown that day, but this I have added to the lecture slide, meaning not lecture, this, yeah, the lecture slide which I had asked Prakash to distribute, meaning keep in the folder. So it should be there. You can look at this slide. So the basic thing is that if you have two antenna interferometer, you can see the left side, the path is delayed by an extra distance, which is d sine theta, given the theta is measured from the perpendicular direction. And if you do that, you can essentially find that there is a delay which is proportional to dl. D, of course, you are assuming that where the direction where the angular offset is in the same direction, the baseline length is. So using that, that is what I had essentially asked the question that, okay, this we know. So so using that 2 pi by lambda into d delta theta, now sine theta is equal to delta theta, sine theta is a theta when the angular offset is small, which I had ensured here in the three baseline files. So these three files which I have given you are basically, if you look at these files, you will see, I believe there would be again RR and LL, those the things will be there, but you will effectively be able to see the phase as a function of time they are going. And so that is what you are supposed to now see, that the D will be given also in that, meaning it will be given as U and V. Now, I have given you in that question, I believe that the offset was introduced along north. So that means if you remember the definition, I believe, which they should have done in his course, that is what is U and V in the basic interferometry. So the V is measured is basically D, the distance of the baseline measured towards north, which is V. So you have to check at V and see that the phi, which is 2 pi by lambda, lambda is 1.4 gigahertz, or you can convert it equivalent lambda, which is 0.2 meter or so. And then V is basically effectively D there, because that is in that direction along north, and times delta theta. Delta theta is unknown, but you know phase, you know lambda, you know effectively dv, d per the underscore v. So that is what is the case. So once you know, you should be able to determine what is the offset. The reason I have given three different baselines was meant that these offsets you can even find from a single baseline, but from a single baseline, the one does not know whether it is unique, because there could be other issues. Suppose there is calibration or some other issue which has gone wrong, which has introduced a phase. How do you know? So if you have three different baselines and you find that this effectively the phase increases proportional to baseline length is what you need, because that will basically give you that. One could have also done a different thing, which is the giving the spectrum and find that as a function of lambda, the phi changes. But again, because your data is narrowband, I have not gone for that. I thought the best will be to give you three different baselines and just check that it is proportional to D. So once you can show that, because lambda is fixed there, that it is proportional to D, then just dividing the phase by the D will give you effectively something which is just a function of delta theta and 2 pi by lambda. So that's all you need to find out. So is this now clear?
Yes, sir, it is clear now.
Okay. So in fact, I will just stop sharing right now, but I will just open the file and also check whether there is any confusion there in that file. Just let me see once.
Sir? Hello.
Hello.
Yeah. So in the for the files provided for the experiment 3, I mean the last experiment.
Yeah.
Yeah. So the file contains UV and W files and the offset files.
Yeah. But so basically, if you
Yeah. So,
open that file, like I have opened the one which is 1822 minus 096 dot h1 dot offset 4 meter 1 dash 16, which is using the baseline 1 and 16. So I can even do a share, but yeah. So that I'll just do a screen share right now. Yeah, so this window you can see, I don't know whether it is readable from your side, but basically there are things like U, which is given in kilo lambda, like 18.29, V is given also, which is 8.42. So what you need to look at is V, because that is the distance along north, measured along north. And then your phase, which is coming from RR, phase which is coming from LL. You can either average them, or you can do it separately, whatever you feel like.
So it is given for like 4 time samples. So
Right. So the reason I have given for 4 time sample is because suppose one data point is affected by the radio frequency interference. How do you know? So the phases, because
okay,
these are
okay.
time separation is small, like first day 07 hour 30 minutes in GMT, then it is changing every 17 seconds. So the 7:30, 01, 17, then 33, then 49. Four such data points are given so that you can get a consistent view. In principle, you should take an average of all these 4 points in time. Maybe you even can the average the polarization. And as I can see roughly that the phases are all roughly constant, meaning they are not greatly varying. There is a variation of about 10 degrees or so, but that 10-degree variation is okay because I don't see that as a problem. It depends on the signal to noise ratio of the source. A variation of the order of 10 degrees is not a problem. Okay, and once you are averaging them, it will go away. Those meaning those variations will go down further. So that will give you one baseline 116. Now, if I open the other one, which is 1 2, the phase will be much smaller. Yeah, the phase is like minus 30 degrees. So 1 2 baseline versus 116, the phases are smaller. So how much smaller? It depends on the V value. So here it is about 0.1. There it is
Yes.
about, there it is about 8. So about so it should be ideally 8 times more. Now remember, one has to be a bit careful here, that there could be one issue which one has to be careful, is that once you have a number which is more than 360 degrees, you will not be able to see that. Okay, so that one has to look at n pi also. You can have an issue of n pi, that is a
Okay,
n pi
okay.
wrap. So that is 360 plus this number. So you could have situation which is 360 plus, and that could basically, let me just look at the other one also. Yeah, phase is here 35. Yeah. So I believe that you have to take into account n pi also, that you can have a n pi wrap, but consider that you have to assume n is equal to 0, meaning the n pi should go to 0. Without that, you can't solve for the baseline 1 2, which is the shortest baseline given to you.
Okay, sir.
Okay. So 1 2 is the shortest. Now you expect, yeah. So let's see once more. 1 2 baseline number. You have a V of 0.08. So you expect 10 times the phase. So roughly more than 10 times, in fact. So 30-degree phase would go to the 300 degree, for minus 47 will go to 470 degrees. So yes, it is order of magnitude looks okay to me, in the sense that you have more than 360 degree perhaps when you are coming to 116 or 130, of course.
Okay, sir.
Yes.
So
So
from the phase lag and V, we need to calculate the angle.
yeah, yeah, right.
Okay, sir. Okay. So should the angle should be same or
Yeah,
it
yeah,
will
of course, because this phase, it is effectively the source has moved in the sky.
Okay, sir. Thank you, sir.
Yeah. In fact, you can even yes. So let me just tell you one hint I have already given, that the delta theta is much less than 1. That assumption holds good here. So delta theta is not large. That I can tell you. That's the hint already. Yeah. So is Desh back? I thought he was telling something, but he got cut or something.
Yeah, no. I think I was just saying that if they want to discuss anything,
Hmm.
we can do that probably after their presentations. so that there is no distraction. One can
Right.
concentrate on just the learning part, right?
Right.
Uh, that can be arranged informally, formally, in any manner, right?
Right.
Besides, of course, some bigger thing that Chetana was proposing, that will require some real thinking and probably some discussion, as Prakash said. So it could be one of the corridor sessions after the presentation and all the rush is over.
Yes, sir. If it is possible, we can have an hour or so session after the presentation.
Yeah, I'm happy to do that. If you
Very
fix the
small things, very
common time,
small
yeah.
thing. The only condition is that you should be there on the blackboard. Sorry, I am putting a
Yeah,
condition
the
there.
Blackboard aspect, I mean, if people could suggest me a tool to draw things and so on, I can,
That
uh,
Prakash sir will take care of,
huh?
probably. Prakash sir can take care of that.
Yeah. I'm not in any institute right now where I can go to
Oh,
the board.
okay. Okay.
But I think in words it can be done largely, okay, and with some pictures. It's not difficult.
Okay.
I think essentially if we, talk about the gist of it.
Meaning we want to see the screen also and we want to hear you also, so that we everything is in sync. What?
Yeah, let's see how best that can be done.
Yes. Okay.
See, to me, what Chetna is saying will be more fruitful in that way if that can be done then after the corona thing, because what she is wanting is more like a classroom experience, but then one has to sit physically in the classroom.
Like, sir,
Because
when we teach in our college, we are using a Vacom or a, and then it is very easy to use whiteboard. So is that kind of thing be arranged? It is as good as a classroom thing.
this what she is saying, if you are interested, you can do, but I don't know how easy it will be for you, because the thing is one has to then work it out and record it either through a mobile as a video or through a camera as a video, and then upload it in the place where they can see it.
Or maybe I'm becoming very stubborn and rigid. It is okay. The anyway, their sir wants to explain.
I think the thoughts can be conveyed pretty effectively, okay, and some examples can be shown. The working out on a board is not as essential at this level as you would find. Okay, once people are tuned to it, already it becomes that much easier.
Okay. Yes. Sure.
So I leave it to you people to work out a convenient slot of an hour, okay, where we can go through some parts of it, and if that is helpful, then one can think of other times or a bigger workshop or some such thing that you are proposing. But to deal with the existing doubts and clarifying them as far as possible, we can have a session after the presentation and all the rush part is over.
Do any other group have has a question?
Yeah, I mean, though most of our questions have been answered when you were explaining in detail, Chetna, and we all went through the slides. It's just that when you said the right polarization and left polarization data is exactly similar, it was, I mean, we couldn't see that through the data set when we plotted it. I don't know if my students are still there online, because we wanted to show you actually the plots for the two polarizations, right?
Okay.
And the data actually looked different.
Yeah. No, I saw that. The right now when I do that, like for example, baseline 1, 2, the sorry 116, the
Hmm.
phases do vary from the one timestamp to another, by about 10 degrees or so, 10-15 degrees. But
Yeah.
that is partly to do with the signal to noise ratio. So that means that if you have a source whose signal to noise ratio is 10, you know that, or you would expect that, then one, meaning effectively in phase, you can have a variation of the order of point 1 radian. So which is about 5 degrees, 10 degrees of that sort of variation is possible.
Okay.
So
So I think,
because these are each 16-second integration I've given,
yeah.
I believe that the signal to noise ratio is still good enough to use the individual data points. So that is the way. And but you have to keep in mind that when you are doing that, you can have an n-pi ambiguity in phase. So that you have to keep in mind. So you can, in principle, give an answer which is consistent with for all three with n unknown. That can happen.
Right.
Okay.
Yeah. I think, but Sahil, are you trying to share something? You still want to show something? Then maybe you can. No, that's fine. He's saying it's okay. Yeah. So then most of our things are sorted out. That's fine then. Thank you.
Okay.
Yeah.
Prakash, anything else? Okay.
Sir, I want to ask, can we have Ruta ma'am for a while? Not here, ma'am. If you can ask her to come for a while, because I guess like I'm having some problem in the GMRT data set. So if she can clear that.
Can we in any case share it uh, if someone can help us with that,
Yeah, yeah,
if you
yeah,
don't
yeah.
mind? Oh, yeah, so
Okay.
then maybe we can share it and we can have a look. Sure, sure, yeah, 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 thank you. Yeah,
Or even Shubhashish might be able to help with certain.
right.
So
So, any,
while there, if you want to share it, that might be helpful. Then we can
yeah, we want to
just,
share it.
yeah.
We actually, thank you. Sahil, are you
Shall,
sharing? Sahil, are
yeah,
you?
yeah, yeah,
Okay,
yeah, ma'am. Yeah, yeah,
right.
ma'am. Wait, I'll just join it from laptop.
I'm sorry, but I think you'll have to wait for a minute. He's joining from his laptop. It's just 2 minutes.
Oh, am I audible? Okay, okay, sir. Sir, is the screen visible?
Yes, Sahil, yes.
Yes.
Yeah. So, sir, I got this dynamic spectrum from the GMRT data. So, initially I got something else while taking like 1024 points, but then uh, right now it's not like transposed. Initially, I transposed the data and I got. I'll just show you what I got initially. Yeah, so I received this, but then Ruta ma'am said that there's some uh, problem in the axis on the y-axis and the x-axis. So I'm not sure that what she was trying to say.
No, the in principle doesn't seem to be any problem, except you need to label and identify the axis, which is the frequency axis and which is the time axis.
Okay, so sir, sir, for the reshaping, I use sir 1024 by 4096 points, like the matrix of 1024 into 4096, and so the output axis, the output matrix after F50 would be 1024 by 2049, right?
Yeah, the time, the number of times you take the transform will remain the same. Okay, that will be
Yeah,
the time.
but sir, the number of the number of points for transform, I didn't took it. The by default whatever numpy takes, it was that only. So I didn't change anything here. Like
So
the n equals some
you would have
number.
given one number at least somewhere to decide the reshaping.
No, sir. The reshaping has been
N.
done here, sir.
The N is what?
Sir, n is 1024.
So that is the shaping. Okay, so
Yeah.
that it took chunks of 1024 points, which took a transform of 1024 points, which gave you 512 channels on each side of the spectrum about zero. Okay, which you might have retained.
Um,
So you would
not,
have
sir.
used about.
That didn't happen, sir. That's what, sir. That didn't happen. So the output which I got was it was 24 1024 into 2049 points.
I see. In any case, the basic thing of the picture that you expect in the dynamic spectrum looks okay. You might have to look into exactly what you did in terms of number of points used for a given transform.
Okay.
Okay.
So, sir, I want to ask. It's a basic question, so sir. I reshaped the data into 1024, comma, 4096 points. Okay. So, the number of points which F50 will take will be equal to 1024, right?
Yes, based on
No,
what coding you have done.
but sir, the thing is, if the number of points should be 1024, then the number of output should be 513. But here I'm getting output as I'll just show you the output. Yeah.
No,
So
I think the
output is
C11 divided by N
hmm,
will be the number of transforms you will be performing, right?
okay.
So whatever that number was, okay, total length of the data divided by 1024 will be the number of times you'll be Fourier transforming. And that should be the time axis label indexed.
I guess then. But sir, if I do that and take the transpose,
So
like while plotting it, if I take the transpose, then sir, I get this sort of plot.
that's okay. I think from this, it appears like you have, so which is the frequency axis you have? Is it the y-axis, which is the frequency axis here?
Sir, I guess y-axis should be the frequency axis because
And that
which
you can check by the shape of the spectrum, where you will see a natural spectral shape. That is the axis along which you have the spectrum. And it's also consistent with some of the RFIs remaining constant over time, right?
sir, I'm not sure if I'm able to follow what you said.
Here in these pictures, the y-axis looks like the frequency axis to me.
Okay.
And that is
Okay.
also because you have taken a 1000-point transform and you will get 512 points as the output.
Yeah. Yes, sir. So, sir,
Okay.
I'll.
So that is one. And second, the leftover things.
It's just that his zero, Sahil, you have to
Yeah.
your zero
Zero
here.
will
That's
coincide.
the problem. The zero has to come down.
See,
Ma'am,
Python does that. Python puts the axis origins
Yeah,
independent of each other.
yeah. So we have to set the origin at that point in Python. Yeah.
It
but
should be
sir,
origin to lower.
okay. Is there a thing origin to lower?
Yeah. Origin equal to
S
inverted
S
comma lower.
Okay. I'll just do it. Okay, sir, it's 0 to
Okay.
4096 and 0 to 5. But sir, the thing is, right now, sir, the spectrum is looking something like this because initially, the horizontal lines, the horizontal shading lines were vertical when I did the
That's okay.
transpose.
Yeah, it should not. The information is not changed as long as you know what is the frequency axis and what is the time axis.
So
In this particular case, now the horizontal axis seems to be the frequency
frequency
axis.
axis, yeah, yes, sir.
Right. So, what is the question?
Yes, sir. So, sir, what Ruta ma'am, sir, what Ruta ma'am said. Hmm. Yeah, so sir, Ruta ma'am said that there's some problem in this plot about the axis. Like this is the same plot which I received right now, but the thing is, ma'am said that this plot was looking okay, but the problem was with the axis of this plot.
Correct. I think we just sorted that out. Two things we identified, which is the frequency axis,
Okay,
right? And
okay.
shifted the origin so that the sense of the increasing frequency is rightly represented.
Oh, okay, sir. Then
I don't see anything terribly wrong with the pictures that you've been flashing. Okay.
but then, sir, Ruta ma'am said that the RMS and the mean should correspond to this dynamic spectrum, but I don't think so that this is corresponding to this.
Why do you think so?
Sir, because initially where the shaded region was greater, the peaks were high, but right now I can only see the sir.
Yeah, I think it corresponds pretty well. In fact, if you just, instead of scrolling up and down, if you could view things, both of them in the same picture,
Okay,
right? You could put the line plot right below the 2D plot aligned with the horizontal spread. Okay. And you would see the correspondence pretty well. The two RFI peaks will coincide, right?
um, sir, RFI peak would be
Persistent
this.
RFI, the persistent RFI, which is seen below about channel of 100, right?
Sir, this you're talking about this one?
I'm talking about that spike.
Yeah, this
And
spike, sir.
spike will correspond to the persistent RFI seen below index of 100. You see a vertical line?
Over here, sir.
Yes.
Okay.
That is that feature. The next feature is the another peak, which is tall, right? Which is between 300, more like 330,
Yeah,
right?
over here, sir.
Right.
Okay.
Okay.
So, sir,
And things
these
like,
are the RFIs.
well, that we believe because something that is remaining constant and it's narrow in frequency, right? Can either be a spectral line, right? And that's why the statistical test needs to be computed. If it was a spectral line, you will find the expected RMS by the observed RMS will still be close to unity, okay, even if it's a
Okay.
spectral line.
Okay.
I mean, even if there is an enhancement of intensity at those frequencies, it will have the same Gaussian native statistics, okay, which will reflect in the ratio of expected RMS to observed RMS. Whereas RFI will not have that tag of strict Gaussianity.
Okay.
And what you will find is on the spectral line, if it's from the sky, you will find the mean and RMS will scale the same way. Okay, whereas the mean and RMS will not scale the same way in the case of RFI.
But if we look at the values that we've got in the plot below,
Yeah,
Yes.
yes, sir.
if we look at the ratio of the expected
Correct.
RMS and
Correct.
so
You will see different behavior at the locations of the spikes.
Uh, yeah, I guess yes, sir. Because thing
No,
is
no.
like,
If you compute the ratio, right now it's very difficult to make out.
right now we don't have the ratio, so we've just computed this is just our observed RMS
Correct.
that we've calculated from our data.
Correct.
Yeah.
So if you take the mean, which is the proxy for expected RMS at the when the integration is not done.
We've calculated that also. We can
Correct.
plot
Okay.
it. Yeah,
Wonderful.
yeah. So
sir, the ratio means this RMS by mean.
Well, it's the mean scaled by square root of time bandwidth product. Okay.
No. So mean by square root of time into bandwidth into 2.
Yeah, square root of the time bandwidth product. Okay.
Okay.
With a factor of 2 based on what else has been averaged.
Okay.
Okay. And
the
that
bandwidth,
ratio is supposed to be close to unity. Okay. This ratio also can be looked at. One scale factor is missing. Common scale factor is missing. So if you just plot this itself, I can illustrate.
we can estimate that because the bandwidth is given to be 200.
This has to be channel bandwidth. Okay.
Yeah, yeah.
Spectral channel
So
bandwidth.
you mean plotting this XRMS by X mean?
Yes.
I plotted
Okay. So
this, sir.
yeah. Well, it has to be mean divided by RMS, but it's okay. So that I can relate to. So out here, this mean value will be
Hello.
the mean value. The
Yeah.
typical values it will hover around unity.
Yeah.
And the dips will be there when the observed RMS is higher, and that is what is the characteristic of the RFI. Okay.
Okay.
So
Sir,
this is
you said that.
RFI.
Sir, you said that the RMS would be nearly to unity.
But you have not
No,
multiplied
ratio.
by, you've not multiplied by bandwidth into
Correct. That has not been done yet.
We have not done that yet. Yeah.
Correct.
Oh, yeah,
You do
yes,
that.
sir. Oh, okay.
So we can see that factor is roughly 2, Sahil. That's okay. I mean, we'll get it, I think. Yeah.
I guess it's the same
Yeah,
thing.
your e to the power 6 is probably causing the trouble. Depends on what units you're putting that in.
Sir, it's megahertz.
No.
It's
200
hertz.
megahertz. Yeah, it's not 200 megahertz. It's the channel bandwidth. So divide that by the number of channels.
Okay, yeah, okay. Divide.
Okay.
513
Divide that by
channels.
512. Yeah.
512, yeah. 5.
No.
513, sir.
No, it is bandwidth divided by number of channels, Sahil.
Picture. Okay.
Sir?
Your integration time has to come into picture. Width has to come into picture for individual channels.
So, sir, this would be like total bandwidth by 513.
Correct.
Okay.
Times the integration time per spectrum that you're using. Okay.
So, sir, the total, the
Because
integration time
sometimes
means.
you might have integrated, right?
Okay.
I think we'll get it correct because that is going to be 2. That's going to contribute a factor of 2, which I can see.
Yeah.
Because
Sir,
otherwise,
but
the scale factor was roughly
Right.
yeah, so it's fine. I think that's now I get it. What we were.
Okay. So
ma'am.
then the dips associated with it are good indicators of RFI.
Okay, sir.
And when this ratio is above 1 in the correct units, it also shows you that the expected, the observed RMS is smaller than expected, which means there might be some constant contaminant. Okay.
Okay.
It is not changing much. So both ways, the excursion beyond unity, okay, on either side of it, indicate a non-sky signal.
Okay, sir. Okay, sir. And
Reach
sir,
of that will be different.
this is the final average power spectral density. Hello.
Yeah.
Yeah, sir, this is sir the average power spectral density. Sir,
Yes.
while doing the cross correlation and the autocorrelation, both were looking same. Any particular reason for this?
Well, it depends on what is dominating. If the source is dominating, if the source contribution is dominating in the spectrum, and if the RFIs are common, right, then they would correlate and give you similar picture as the total power self correlation.
But sir, sir, there's one thing that in the cross correlation and in the autocorrelation, the Y scale is almost halved in the case of cross correlation. So here it's like 8 lakhs. Yeah, here it's 8 lakhs, and here it is around like 1.0 into 10 power 6. Um, reason for this?
Well, it's 1 million, right?
Yeah, 1 million, yes, sir.
How does it compare on the scale?
So compare as
Why
in?
don't you plot them on each other?
Oh, okay, I'll do that, sir. Sir, here it is. Here it is.
Okay. Now, what is the level of difference you're talking about?
Sir, this difference, sir, from this peak to this peak, or from peak to peak difference.
Yeah, but you do expect changes, right? The spectrum you get in the total power individual dishes has contribution from the receiver noise, right? It has contribution from the receiver noise.
No, sir, but sir, I'm not getting your point, sir. Sir, there's one plot about the cross correlation and the one is the autocorrelation. So I'm not able to.
I'm saying the cross correlation looks for similarity between the signal.
Okay.
The receiver noise from one system, one dish, is not related to the system noise from the receiver noise from the other dish.
Okay.
Only common thing between the two is the signal coming from the sky.
Okay. Oh, okay.
So the blue shows the signal coming from the sky.
Okay.
In contrast with the sum of what is coming from the sky and what is produced locally. So the difference is what is produced locally.
Okay, sir.
I mean, this is a naive understanding based on a simple question. One will have to make sure that they are on the same scale.
Okay.
Right?
Okay, sir.
Gain difference and so on and so forth. So you can put two self spectra on top of each other and also show the cross spectrum. And this will clarify for you. Okay. And when you take the difference, also plot the difference.
Plot the difference. Sir, plot the difference between cross and autocorrelation.
Yeah.
Okay,
that will
sir.
show you the, ideally what you should do is take the two power spectra, self spectra, take the geometric mean of it.
Geometric, sir, I'll just write it over here.
Take the product of it, take the square root, and then subtract that from the subtract the cross correlation from that, and that will leave you a contribution which is purely local.
Okay, okay, sir.
Because you know that you are actually taking, product of the two. So the square root of self spectrum, okay, in both cases are effectively multiplying, right?
Yeah, yes, sir.
If in terms of gains and so on. So that will do a sort of comparison, which is comparing apples with apples.
Okay, sir. Okay, fine, sir.
So I shouldn't tell you too much in terms of make you also think of the differences, but I'm illustrating you the essential differences that might arise. Okay,
Yeah, yes,
the
sir.
reasons for it. Okay, and then you think about how to extract them,
Okay,
or
sir.
whether they match.
Yeah, okay, sir. Yeah. Thank you, sir.
Okay, good.
Yeah, thanks.
Hello, sir. Our group also had some doubts with the GMRT spectrum. We obtained the spectra, but there are parts where we are not pretty sure about the plots. Can you please go through them once? Then I will share my screen.
Yeah, yeah. Ideally, we should get Ruta to also. She will also be happy to see the progress. But I'm happy to try to answer any queries in the meantime. Please go ahead.
Yes, I'm sharing then. Oh. Sir, is my screen visible yet?
Yes.
Yeah, so basically I was processing the band 3 data of the GMRT which Ruta ma'am had provided, and so this is how the actual data looks like voltage versus
Yes.
of channel 11 data, and this is the channel 12 data. Now these histograms and stuffs, I guess they look pretty fine. Now
Okay.
so I'm proceeding to the dynamic spectrum part. Yeah, first of all, so here, I have considered 4096, as ma'am said, to utilize the total resolution which is available. This is the number of the voltage samples which I'm considering, like
Yeah.
Fourier
Okay.
transformation.
For
And
each, for each section that you
yes,
Fourier.
sir, exactly for this section. Yeah.
Okay. All
Uh,
right.
yeah, and also, I thought that in order to enhance the resolution, later after obtaining the Fourier this for each spectra, this thing, I was going to add the number of consecutive spectral samples to obtain a stronger resolution, as I did for the VIII also.
No, it will not make it. The word of stronger resolution is
No, for a better
not
intensity, what
understandable.
I meant. Yeah.
If at all, in fact, by integrating, you're reducing the time resolution, but you are improving the signal to noise ratio.
Yeah, that's to improve the SNR to
Okay?
obtain a
Yeah, you get a better contrast,
yes, a better contrast,
a
exactly.
better accuracy in the measurement. Yeah.
Yes. So
But you don't improve the resolution. You,
yeah,
in fact,
resolution
weaken the
cannot be done.
resolution
Yes.
in time by averaging. Okay.
Yes, sir. Yes, sir. Here is the amplitude versus frequency of the channel 11. Like, uh,
Right.
so this
Yeah,
is
go
how.
ahead. Hmm.
Is it fine, sir?
Well, I don't know. It doesn't look. It doesn't perturb. Uh,
Okay.
right.
Okay. Yeah. And this
I
is for
hope you
channel.
have removed the DC before transforming further things, so that the
Yes,
nasty
sir. Yes.
first point is not spoiling your
Yeah.
play contrast. Hmm?
Yes, sir. That has been done already. Initial histogram part, I have done that.
Okay, very good.
Yeah. So
No,
after.
from the data also before transforming, it's good to subtract a mean from the voltage data. Okay.
Okay, the mean from the. Yes, sir. That has been done. That has been done. Madam asked us to do it in a previous
Right.
section.
Right.
Yeah.
Right. Okay. Very good. So
Yes,
go
sir.
ahead.
Yeah, after this, now I'm progressing towards the dynamic spectrum, and this is how my spectrum looks like. I have,
I'm not able to see either. It's my screen browser. I'm just seeing a black patch.
no, sir, there are lines
I don't see any. I see
okay,
nothing except a black patch.
Yeah, same, sir. It's a black patch only.
so is it due to the resolution fit? I will,
But if
I
you
mean,
zoom it, then you might see something.
No, no. Also choose the correct scale. I don't know what scale you've
But
chosen.
the scaling is not right. We were, I mean, you should.
If good to find the min max in the data itself, unless it does it automatically. And
okay,
it's also possible that the first point, first row,
yes, yeah,
or the first column, depending on which way you plotted the data, the first channel spike might be stopping you from seeing all the details of the rest. So
Sir,
please get,
Yeah.
it might appear even in your dynamic spectrum as one line. Okay.
Okay, sir. Okay.
That
Yeah,
is one
like
possibility where you might be stopped from seeing at zero frequency.
Sir, actually, I got a similar graph yesterday. The madam asked me to remove the first point,
Correct.
upon which I got a kind of sync type of graph. Then madam said
The
that
first point
it
should
was
not be,
wrong.
it should be just a spike.
Yeah, but even after
Unless you have
remove,
windowing function, okay, which is narrower than the length of the Fourier transform, you will
but
not see a sink. Okay.
okay,
sorry,
like
sir, can you repeat again?
To see a sink
Yeah.
function of certain width, the width has to be wider than the interval in whatever domain in which you are seeing the sink. Correct?
Yes.
If that is so, it will automatically imply that there is a windowing function, okay, effectively, which is narrower than the length of your data you're Fourier transforming.
Okay.
okay, sir. Like for once,
And
I'm
unless
yeah.
unless you have applied such a window, which you wouldn't want to do, you wouldn't see a sink function in the other domain, okay, as a response function.
Okay.
Okay, so here, if you can just subtract the DC, okay, take the mean, or even while plotting, put zeros at the first column or row.
Yes, sir. That's what I'm just trying to do now. Then I'm just wanting to show you how it looks like.
Yeah, then you yourself will see dramatic improvement.
Okay. Okay. So, let's see. So I'm just doing it here.
Wow, it gives you help as you type. That's very impressive.
Yes, sir. Sir, I'm basically setting all the elements of the first row like to 0 because
Well, yeah, as long as you're sure it's a row and not a column, it's fine.
yeah, there were. I guess I did some error 1 minute. So, what is it? Okay, okay, okay. I
Sir,
got it. Yeah.
You have to add one more bracket over
You
there.
need a
Oh
round
yes, sir.
bracket
Yes,
there.
sir.
Yeah,
Yeah,
bracket before column.
Yeah, one more bracket instead of the
yeah,
colon,
yeah, yeah. Got it. Yeah,
or before the colon. Yeah.
yeah. Now I guess it should be fine.
No, no, no. You added one extra on the left side unnecessarily.
Okay. Yeah. 1, 2. Yes, fine. It's still there.
No, that spike is
You know,
there.
it is
You,
in GMR,
you,
in this data, it is not at zero. It's, if you make it little bigger, it's not at zero. You
I
can
see.
see that.
Oh,
Yeah,
so that's why this person was saying it's looking like a sink.
Yes, it's not at zero. I mean,
yeah.
I saw that.
It's at 1 or 2. Yeah, it's at
Yeah,
1.
you just make it bigger. You'll be able to see it.
Okay, it's
Okay,
not the first row then. Okay.
maybe it's a then it's probably some labeling issue in the Fourier transform where the data corresponding to zero frequency appears. Is there some indexing issue of 0 and 1? You know, indexing starting with 0 or indexing starting with 1?
Okay.
So as far as this array goes, it's always from zero, but this particular
So
is
what
not.
is the contribution at 0 really? The first point, is it low or high, or 2 points are high?
Sir,
Yeah.
l-
What I
Like
remember seeing was that 0 was low and 1 was, it was at 1 where you could
Okay.
see it.
Sir,
So that's
actually, if we
actually,
have adjusted the mean in the histogram, that the peak there should not be a peak at 0. It should be 0. No? I mean,
yeah, even reject the second point. Nothing is
Actually,
lost by.
Soumya, you could clip while
Yeah.
plotting the graph actually. Like you could, as clip the data file by plotting the data here. You could select the
Uh,
points here, right? You don't need to change the whole thing.
Sorry, I didn't get you. Can you please repeat it once?
No, you could write the, you change the zero value in the starting, right?
Yes, yeah,
Yeah,
exactly.
instead
Yeah.
of that, while plotting in the last line, you could, only choose the data excluding the first 2 points or something.
So what you can do is
hmm.
here in fx put a
Yeah,
square bracket.
square bracket and something two
Yeah,
to the last point.
yeah. So 2 colon and
Yeah,
after
colon
no no
after.
No,
square bracket.
square bracket,
Yeah.
two colon
Right here
and leave
one
one or two, anything.
one or yeah no
No,
call
first,
before
first
colon
Double
before
colon,
colon.
double
before
colon,
colon.
Yeah. Okay.
Yeah,
Yeah.
and put
Colon
a colon. Yeah,
and leave
and
them.
then just
double
yeah,
colon.
and
The
just run.
no. Then copy the same thing to the next thing.
No, remove this or
A
remove the
single
column.
a single
Yeah,
column. Yeah.
and do the same thing in the f average.
Okay. Okay. Got it. Like we are just discarding the first place. Yeah.
Yeah,
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 yeah, yeah.
yeah, exactly.
You are just doing the slicing and plotting it.
Okay. Fine.
Right.
Is yeah. One point
Yeah.
is bit reduced. I
Instead of
guess.
1 point, try 2 or 3 or something.
Yeah.
Yeah,
Yeah.
yeah.
Exactly. Exactly. Yeah.
Yeah,
Still,
it's getting better. Like,
it's getting better. Like
yeah,
it has reduced a lot.
yeah. If you For my data, it was like actually exactly at 1. When I removed the first point, it just happened to
Yeah,
be at minus.
yeah, same happened with me. It was at one only for me as
Yeah.
well.
yeah, for me too. But
Hmm?
for
Maybe.
B15, I am said it was wrong for channel 2.
Okay, okay.
Okay. So like if I do that, I guess the spectrum would also develop.
Yeah, it will develop.
Okay. So that I can do later on. But I had another query. Here.
Sorry, I got disconnected just after you made the small change in your code.
Yes, sir. Uh, yeah, after that, like the spike got a bit reduced because now we are considering we were just removing the first one or two
Yeah,
initial rows,
I
and
think you should check your code by simply giving a constant value at the input of the FFT and seeing where it comes in an array. Okay.
okay, sir. Okay, yeah.
I have doubts about certain
Mhm.
other things might be playing some mischief, because a simple DC offset should result in only the zeroth frequency. Okay, zero frequency component being non-zero, and if it spreads over 2 channels, it's already an indicator of, you can think in the Fourier domain. If something is that wide, that means there is some function in the other domain which is narrower, or whose narrowness is comparable to half of the data length. So
Okay.
unless you are taking only half the data length, okay, and putting zeros and then taking Fourier transform, right, then you will of course see a sink of spread over 2 channels.
Okay, sir. Like I'm just
So
making.
I'm you be careful about what data it thinks it's taking a Fourier transform of. You might have loaded the data in reshaping, okay, only over half the number of points, and you might be transforming twice the number of points, in which case it will take one from the column or row of a reshaped array, and rest of them are assumed to be 0, in which case it is like a window function of where you have the window spreading to half of the data, that is Fourier transform, and
Okay.
rest of it is being 0, and of course that will result in a sinc function of width 2 channels. So all that will fall in place.
Okay, sir. Like I'm just.
So good thing is to do a test by putting all ones in your array, okay, or the reshaped array, and then seeing what transform you get.
Okay, sir. Fine. I will see that. Yeah. And another thing I don't know, like if others observed or for the band 5 data, I saw that while processing with the data, like for that the SNR was pretty high for the band 5 data as compared to the band 3 data. Is it actually so? Like if any,
Higher by how much? Higher by how much?
so like
Factor of 2?
I guess it was higher than 2 factor of Wait, sir, I will verify once.
Is it the signal to noise ratio or is it the noise level?
Sir, I will say the noise level was pretty higher than what we.
Was the mean also high?
Sir, for that, I will just
See,
verify. Yeah.
because the gains can be different in the two antennas. Okay, that's not unusual at all. Okay.
Okay.
What you need to see is the relative fluctuations relative to the mean value, whether that was very different from one antenna to the other.
Okay, sir, I will see that.
Even that can differ, but not by so much amount in general. I mean, if such a thing occurs where there is huge difference between the performance of one receiver with respect to the other, generally you will find that engineers would like to go back and test it out and fix it. You would the general expectation and desired situation is where all the dishes are performing similarly.
Okay, sir. And sir, another thing, like for that data, we were asked, like if we considered only the magnitude of the voltage signal rather than the phase, what will happen, and how the spectrum will vary from the original spectrum.
Right.
So what I observed was that,
And in the
yeah,
case
yeah,
where only the sign is kept and
yeah,
the
phase
magnitude is
exactly, yeah.
drawn.
Yeah. So what I observed that when the only the sign was kept and the magnitude was gone, that time the spectra kind of resembled the original one, like the original data which we had.
Mhm.
And while working only with the magnitude, that time I did not obtain any spectra. Like I didn't obtain anything. It was a black patch.
Yeah, good. So try to understand it.
Yeah.
Black patch. What do you mean by black patch?
No, I mean I didn't obtain any spectra. Like just the noise was there, nothing.
No, but there will be some shape. So there will be something there, right?
Okay. Yeah.
It may or may not resemble your original spectra. This is the line spectrum, one-dimensional spectrum that you got after averaging.
Yes, sir. Yeah.
Compare those, right?
Okay. Okay.
And make
Okay.
whatever statement you would wish to make.
Okay, sir. Fine. I will see
Right?
that and try to get it done. Okay, sir.
Yeah.
Thanks.
None of the things that you described are perturbing. Okay.
Okay, sir. Yeah, only
Right.
that spike, that part I have to reduce, and then I will try with the
No,
data.
also, I think check my suspicion, even in the case of Sarvesh, I think, has been complaining about this sync function being seen. And
Yes.
Gitanjali also just now mentioned that you indeed see that contribution at the second point, right?
So can I show you? Like I'm running this script now.
Yeah. I think yeah. Oh, oh, of course. Oh, yeah, oh, yeah. No. We also need to stop because we also want to, okay. Yes. Okay. Yeah. But in the meantime, I suggest all of you to put some known data like unity, okay, across the array that is reshaped and check out the outputs. Okay. I'm leaving right now and we'll continue the discussion later. Okay. Bye.
Sir, are we going to continue at 6 p.m.? Okay, sir. Thank you.